notes here. We'll go ahead and get up to this screen so that we can see what we're going to be doing here. You'll be able to find these notes if you look into the workspace, go to chapter 3, and then in your resources area, you hit this chapter 3, and it'll pull up the notes. This is the more traditional style notes that we did to kind of pair up with the Pear Deck that we did in class. Hopefully you watch this video, look at the notes. I'll probably put a video up from Crash Course again on ecological population differences. That way you're having multiple ways to get this information on top of your guided reading also. So again, like we have been talking, we're talking about populations and how they are in checks and balances. The first thing that we're looking at here is what is a population. You know, it's a group of the same species living together in the same place at the same time. What are some of the links that link them together? Basically, it boils down to resources. Is there water? Is there food? Is there space for them to live? Is there shelter? What kind of boundaries keep populations separated? That would be, you know, like geographical / natural barriers, like mountain ranges, rivers, lakes, different types of tree lines, major forest groups versus grassland. Okay, those are all natural barriers. Your artificial barriers are kind of going to refer to man-made things such as roads, fences, different things like that. We talked about it when we talked about the movie Over the Hedge. The hedge was a man-made artificial barrier, even though it was natural things. The human beings actually put that into place. For population growth to happen, members of the population have to be present so that they can mate and produce offspring. So that's one of the big things when we talk about population growth, is there has to be enough of a population to be able to create more offspring. When we talk about measuring population, we have two different ways that we measure it. Specifically, what we're going to talk about is population size, which is the total number of individuals making up a population. So if you look at this image here, in year 1, we started with 2 deer. They had offspring, had 2 baby fawns. In year 3, the baby fawns were old enough to procreate, create offspring. So if you see year 4, they have offspring also. And the changes moves on as the original parents still had more offspring year 3 after they had the 2 offspring. So the population is the total amount. Usually doesn't stay the same for long, okay? Now, population density is the number of individuals per area. So we divide the population size by the area it occupies. So if we were going to think about the population density of the county, Montgomery County, which is right here, of deer, what we would do is we would take that population size and divide it by that area. Usually for the larger organisms, they happen to be in lower densities due to the amount of resources that are available. When we talk about their density, we're really talking about dispersion and how they are spaced in the population in relation to each other. We have 3 different versions that we talk about. We talk about random, uniform, and clumped. If you look at them, they all are really based off of how the resources are laid out. Randomly put, you know, some things grow randomly out in the field, so you might see random pockets of them. All right, a uniform area of crops would be more like what we do when we plant them, okay? Or if you were still talking about plants, they might be clumped around different resources such as water, or they get more sunlight in these areas. So those are the ways that we talk about dispersion. How do birth and deaths cause population growth and shrinkage? Again, immigration with an I means population increases when the species moves in. Immigration with an E, we have population or species moving out. So we're going to get a decline with immigration with an E, and we're going to get increase or an incline with the immigration I moving in. Remember, births are what we're talking about for immigration with an I, and deaths for immigration with an E. Okay. Um, you know, populations are going to grow very quickly with abundant resources. We call that exponential growth. And really, this is the beginning part of our S-curve also, if you look at it later. But exponential growth is when a population increases in proportion to its size. When resources are abundant, you have a lot of food space, you have a lot of sites for shelter, it's going to grow faster and faster over time as it goes on, especially if these resources are abundant. Something that we didn't talk about in the pair deck was this per capita rate of growth. That's a comparison of birth to death rates over a set period of time. And ecologists can determine how much a population increases or decreases based off a personal or a per individual basis. Basically, what we're talking about when we talk about population size, it's the current size times your per capita growth rate. Okay, and what we're getting is information to put into a life table, which ecologists can then predict how the population will change over time. What keeps us from getting exponential growth in all different species, you might ask? Okay, why don't we have exponential growth in every type of species? Because we have what we call limiting factors. And the limiting factor is a factor that slows population growth or can even prevent them from existing in certain areas. We break them down into two different versions. It's going to sound very familiar. We talked about these type of things. We have abiotic and biotic factors. Remember, abiotic refers to those non-living factors. Could be sunlight, precipitation, amount of nutrients in a soil, dissolved oxygen in water, all kinds of different things, temperature also. Your biotic, okay, could be talking about trapping, predation, competition with other organisms, availability of food, shortage of mates, disease, parasites, all those things that are based off of living factors. When you look at how they influence density, population density, we actually put them in two different categories, density independent factors and density dependent factors. Your independent factors are your limiting factors that affect a population regardless of the population density. It's going to come into an area and it's going to wipe out everything in the area. Tends to be your catastrophic events, your natural disasters, ice storms, droughts, toxins that are released into an area. It's going to destroy that whole area. Whereas a density dependent factor, okay, it doesn't spread near as fast. Okay, and it's limiting factors that affect the population in ways related to the population density. For instance, disease. If I put a disease in an area, if they are clumped together or clustered together and they can't fight off that disease, that clump is the only one that's affected. It's not a widespread event. Okay, amount of food, so resources, space needed to be healthy. Is that in dire need of competition? Those would be density dependent factors. And talk about compensatory mortality versus additive mortality. The compensatory, different causes of death that make up for the mortality that would naturally occur in a population. So it's not going to change a population size to decrease over time. This is something that is naturally happening. So that's why we say it does not cause a population size to decrease. Different causes of death compensate for one another. So they all kind of add up to what we would predict them to lose anyways. Now, the additive mortality is death that adds to a population's overall mortality, and it does cause a population size to decrease over time. These are the extra kind of mortality rates. The last thing that is in the chapter that we need to talk about is carrying capacity. As you can see, we start again, like I said, with that J curve. But as we hit this area that we call the carrying capacity of this population, what's keeping us there or what's putting us there? First of all, we need to understand what carrying capacity is. It's the number of individuals that a given area can support at a given time. And that's based off of our factors, our limiting factors. You're going to get an initial burst of population growth, that exponential growth. But as that population gets around its carrying capacity, it's going to either be right on that carrying capacity or a little bit above or a little bit below. When the size gets too large, the population gets too large, there's higher competition for resources. When there's higher competition for resources, that means there's less resources. So you're going to get a natural dip. Like I said in class, it's kind of that predator-prey relationship graph where you get an influx of prey, it goes high, and then your predator population will rise also. Once the predator population gets to a certain point, though, we see the prey population decrease very rapidly. So instead of predator-prey, we're talking about population in response to its different resources. So the resources is what really drives the carrying capacity, those limiting factors. Do they have enough food? Do they have enough shelter? Do they have enough space to live in? So when we think about carrying capacity, don't think of it as a certain number. It's based off of more than just, well, I can only have X amount of organisms in one area. It's different for each area. If I have a lot of water in one area and a lot of food in one area, that carrying capacity could be higher for a specific organism versus if that same organism was in an area where there was not as much water or not as much food. So it's based off of those resources that are in the area that they are. So hopefully your understanding of this chapter can be done by either looking at the notes, watching the crash course video, watching this video, or again, I might be able to release the Pear Deck if we need to do that. So please study, please look at the information, watch it multiple times, and get a good understanding.